started. All right. Scott and Joel, you guys ready?
I'm ready.
I am. I'm good.
All right. All right. So I'd like to welcome everybody to the CREATE webinar on solar PV battery storage and charge control. I'm Gabby Temple, the project manager for the National Science Foundation Advanced Technological Education CREATE Energy Center, and I'm one of the co-PIs for the energy storage project that this webinar is funded under. All right, next slide. So just a very brief overview of the background of the project, and we're going to jump into what you are all here for. So in May of 2019, we were fortunate to be funded by the National Science Foundation ATE program to take a group of 16 faculty and industry experts to southern Germany to meet with industry representatives, Germany faculty, and government officials and see firsthand how battery storage was being implemented and the technologies used, and the trip ultimately culminated with the Smarter E conference in Munich. So this lab that you're going to see today was created as one of the activities as a result of this trip and some of the lessons that were learned. So these are your presenters today. You have Scott Litticoat, who is a faculty member at Green Bay Southwest High School, and Joel Shoemaker at Madison College. And, oh, sorry, I advanced one slide too many. But with that, I am going to turn it over to Scott Litticoat.
Okay. And you can stay on this slide or back up. It really doesn't matter. I'm going to request control, which hopefully I will get here shortly. And that would be good. Hi, everybody. I'm Scott Litticoat, and I've worked with Joel and Ken Walls since 2015, along with Chris Folk. Will run the STEM Educator Solar Institute out of Madison, Wisconsin this year for a 6th straight summer. I'm a full-time teacher at Green Bay Southwest High School. I teach chemistry, but I also teach a year-long class on energy efficiency and renewable energy, for which my students can earn their choice of either technical school or college credits. Today we're going to review a lab that's been developed by Joel at Madison College. It's one we've worked into our summer institute, and one I recently finished putting into a polished written form with what I believe are some really useful features for you and your students. And the lab is battery storage, solar PV, battery storage and charge control. Doesn't look, Gabby, like I have control of the screen yet. Okay, hoping so. Okay, maybe I do hear it. It's kind of looking like I do. So what are our objectives today? Let's just review them real quickly. First objective, understand the function of the charge controller in governing current flow in a renewable energy battery storage system. Joel will be covering that mostly, as well as the next one, predict, measure, and explain electric potential and current in a variety of dynamic settings. My part, which will be the shorter part, which will be the leadoff part, understand how to access this lesson and a bunch of others on the CREATE website. And finally, understand the features that are going to be hopefully nice and available to you within this lesson and the other lessons that we've got on the CREATE website for ease of teacher and student classroom use. Okay, so if you didn't know, and you probably do, today you'll learn that CREATE has a website. The URL is real easy to remember. As Ken Walls would say, URL violates the first law of thermodynamics. You can't create energy. There it is at the top of the page. I'm sure you can Google CREATE too, and I'm just as sure that you'll get here. Once you arrive here, you'll see a real cool picture of Joel and me on the Germany trip last year. If you click on teaching materials, you'll be taken to a page that Gabby referred to, but you can see here, there are some questions, real brief questions that are asked for identification purposes, and after completing those, you will be into the website and you'll arrive at a page that looks like this. On the lower part of this page, you'll find that there are already 6 teaching lessons there. And I'd like to review those real quickly for reasons I'll get to in a couple minutes. The very first one, measuring sunlight, the Pyranometer. And in this lesson, students learn how to use this professional tool to examine how the intensity of sunlight varies in several common settings. The second lesson is the Solar Pathfinder. And in this activity, as you might expect, students assess how suitable various sites are for placement of a solar array. Third lesson up on the website is the PV watts calculator. And here students learn how to use this online solar calculator, and they learn how different locations vary in sunlight production and payback. 3 lessons came up last year. Those first 3 lessons have been on the website now for a couple of years. These lessons came up last year. First one, solar PV, silicon. This is a simple, but it's an important lesson introducing students to silicon, its unique properties, and how it's used in the industry. Fifth one is called Watts from the Sun. And with this lesson, students calculate the output of a solar module and size PV systems up to specific user requirements. And as Ken Walls would say, students can never do too many power calculations. The sixth one that's been up there for a while is solar PV balance of system and system design. And in this activity, students learn about balance of system equipment requirements, and they design 5 basic PV types, solar PV types of systems using that equipment. So those are the 6 lessons that are already there, and these lessons have the features embedded in them that we're going to be reviewing in the next few minutes about the lesson that I put together based on Joel's fine work in Madison. So the 7th lesson at the bottom of the page is the one that we'll be reviewing today, and as you can see, it was posted a couple of months ago. Battery storage and charge control. There's a student lesson and response guide and a teacher answer key. When you open up the lesson, the first thing that you're going to see, if you look at the first 2 pages side by side, the first thing that you're going to see is our copyright declaration. And I want to review this real quickly because I think it's really nice. First of all, there's the symbol for the copyright, which is right here. And this symbolizes our copyright. So it shows up on the masthead of the very first page of the lesson as well. And that might be useful because some of you might be in a situation where you can't get a lesson duplicated unless you can show that you've got copyright permission to do it. So on the left-hand side, we've got sort of a declaration page that very simply says, here's our copyright. And very quickly, what it says is you are free to share this pretty much in any way that you would like, and you're welcome to adapt it, which is to remix it, transform it, and build upon the material. You're free to do that. The terms upon which you can do that, though, are these. You have to give appropriate credit to create when you do that. You, of course, it says non-commercial. You may not use the material for commercial purposes. And then it says if you remix, transform, or build upon the material, you must distribute your contributions under the same license, which essentially means you can't adopt a more restrictive copyright than the one that we're here. I'm getting some feedback. Are there people joining us? Okay. So the idea is that this page tells what the copyright is, and then please delete this page before using the lesson. And in this particular lesson, there are some important reasons to do that, which I'm about to get into. So you don't need to give this page to your students. It's just there for you to review. So the reason that you want to delete that is for this particular lesson, the facing pages of this lesson are what I call strategically arranged. So in this slide, you see 2 pages that would be found left and right of each other in like a 3-ring binder or something. And all of the instructions for these 2 pages follow from the diagram that you see there, and all the questions and things to do relate to the equipment situation for the page on the left. So do delete that first page, and the pages will be nicely arranged for you for this lesson. It's not as important in the other lessons. Some other features that you should be aware of. At the end of this lab activity, there's a section called Show What You Know, which is basically post-lab questions, which you could add to, or you could delete some of the questions depending on your specific situation. Another thing that's worth mentioning is that It hasn't been done yet, but posted real soon. I'm in the process of working on this. Going through the lab, I'm combing through the energy literacy standards, the national energy literacy standards and the next generation science standards to see how well this lab matches up with those. And so there will be a specific document within a couple of weeks on that. So people wanting to know how these match up with standards can find that information there. It's already provided with some of the lessons. It'll be provided with all of the lessons very soon. Some other nice features that you should be aware of with this lesson, that there is a teacher answer key available on the CREATE website. I mentioned that earlier. The answer key, as I think Joel will probably get into, might not be as specific. In other words, you might not find answers that have specific numbers attached to them because the equipment that you use might be different than what we use at Madison College, but rather you'll have instructions on how you would determine what the numbers would be for your answer key. The documents for this lab are available as Microsoft Word documents and PDFs. So if you want to use them as originally formatted, you can download it as a PDF, but they're also available in Microsoft Word, and that enables you to alter the document pretty much in any way you'd like, so long as you've got Word available to you. A really nice feature. The document that I put together was written and formatted in Word for ease of translation into a Google Doc. There are people who will do this lesson with Google Docs, or maybe certainly high school teachers. Many of us have been kind of restricted to Google Docs. I wrote this in such a way that it translates to a Google Doc real nicely. Maybe not perfectly, but you won't have to go through and try to change up about a dozen different features that didn't move very nicely from Word to Google Doc. That translation should be pretty easy. And then finally on this slide it says these are written to enable students to record information and answer questions right into the document for digital submission. So if you, let's see, like in my situation, I've got students whose handwriting is very difficult to read. They can word process right into the document and submit the document digitally. They can word process into the document and have it typewritten. Or if you don't like doing it that way, you can simply take the document and reformat it and give students lines upon which to write. It's entirely up to you. I have my students do things for digital submission. And finally, and let's see, I'm going to give back control of the screen here, give up remote control while I talk a little bit here on this last slide. The document that I wrote has a materials list included. Joel is going to talk extensively about this at some point in his presentation. So we have an opportunity here to give you a head start on materials that you might look at if you choose to adopt this lab. But before I turn this over to Joel, I'd like to say that our lessons have been written for use at a number of different student levels. So if you know of or can think of any teacher at any level who might benefit from seeing or using these activities, please encourage them to check them out on the CREATE website. And so with that, it's time for me now to turn this over to Joel Shoemaker.
You got it, Joel?
For some reason, when I had control, I could not see the mute button, so I couldn't unmute myself, but I'm here now. Can you give me back control? That'd be awesome.
Yeah. Oh,
all right.
Sorry.
Excellent. That's quite all right.
I'm working on it. Where's our remote control? Joel.
Awesome.
All right.
Thank you. Great.
Yep.
So,
there you go.
This is Joel Shoemaker. As Scott mentioned, I am going to run through how the lab works, and please ask questions as we go along. There's a lot of steps, and so if you're starting to get lost, you can certainly either speak up or in the chat button ask a question, and we'll be happy to address those right away. We'll take questions at the end as well, but we're happy to take questions as we go through the steps here of the lab. So first of all, looking at the components of the lab, the pieces that we use to do the lab, There is a deep cycle battery, a solar PV module or panel, a charge controller, a load center and circuit breakers to allow us to turn things on and off, and our load, thing that will use the electricity that we're producing and storing, is an incandescent light bulb. And then to measure the various electrical quantities, we have a couple of digital multimeters, and then finally a pyranometer, as Scott mentioned earlier, which is a device to measure light that we use to predict, given a certain amount of light that is striking our PV module, how much current output it will have. Let's see if I can not to be able to control our screen yet.
It says you have control right now, but I can always move it along if you need me to. There you go.
Oh, is that me? Okay, he's zooming right along. Okay, and then to get more deeply into each individual, or a little touch, I should say, a little more deeply on each individual component. The deep cycle battery is, of course, the part of the lab that is storing the electrical energy. We use a 12-volt absorbed glass mat lead acid battery. The reason we use the absorbed glass mat is that it's a sealed battery, and therefore there's no liquid level to maintain or to spill. So it makes it a very safe option. The 12 volts keeps it at a safe voltage, and these are relatively small batteries with just 8 amp hours of storage capacity. And this is done deliberately so that the students in the course of the lab can see the electrical quantities as the battery charges and discharges. So we'll talk about that as we get into the actual steps of the lab. Next, we have the photovoltaic module that is going to produce the electricity. It's a 12 volt or a nominal 12 volt module. The 30 watts, again, is chosen deliberately as a size that can charge the battery relatively quickly, but not large enough, at least in our choice, not large enough to provide enough current to supply the incandescent light bulb by itself. With every energy storage system, you're going to need, or at least with the battery storage system, you're going to need a charge controller. So this is the, in some ways, the unique element of this lab set of equipment that's different from other solar lab setups, the charge controller. And its purpose is to make sure that the battery is not overly charged and damaged or overly discharged. So then we have our incandescent light bulb. This, I suppose the unique thing, or maybe not unique, but the important thing to keep in mind, since the rest of the components are 12 volts, this light bulb is also a 12 volt light bulb. They are relatively widely available because of RVs and other types of mobile living situations where the vehicles run off of 12 volts. So they need lights that run off of 12 volts. So they're not really hard to find. They'll be a little more expensive than you're used to for your 120 volt, but they're not that hard to find. And then the 25 watt size, again, has been chosen so that the students can see the discharging of the battery while the lab is going on. The load center and the circuit breakers provide a location for safely being able to control the different components of the lab, that is, turn them on and turn them off. We use DC rated circuit breakers and the load center that would be used in a full size solar photovoltaic system. But that's not essential for the safety in this lab. So if you chose to use a box with some typical switches that you might see in a house, that would also work to be able to control the different components of the lab.
Joel, I'm sorry, I moved my mouse, so you have to take control of the screen again.
Okay, I think I got it. Thank you.
Okay.
In order to measure the electrical quantities as we're doing the lab, we have some digital multimeters. And the way that we do it is we have two multimeters, one that's set up to measure voltage, and then another one that is specifically for measuring current. You could do the lab with a single digital multimeter. However, when we've tried that, that has been confusing to some students, and it seems like with every student results in as they're switching back and forth from trying to measure voltage and then to measure current, somebody forgets to turn the dial or to put the test leads in the right spot, and so it makes it more challenging. So if you're able to use two digital multimeters, one set up for measuring voltage and the other one for current, that will definitely simplify the process for the students. And then finally, in terms of the components, the Pyranometer for measuring the amount of light that is striking the photovoltaic module, and this being necessary for having the students having an accurate prediction of how much current the module should be producing. We found that as we've used this lab a number of times, that there's a couple of important elements to think about in terms of getting the best results for the students. And the first of those is, if at all possible, do it outdoors in full sun. Indoors, it's very difficult to get enough light striking your PV modules to produce a significant amount of current. We have tried a number of times with different light sources, and it's just very challenging. So outdoors works a lot better. And then the full sun, the most challenging conditions for students are when you have intermittent clouds, because the values will change and that they get inconsistent results, and it's hard for them to understand those results. So even a fully cloudy sky is better than the intermittent clouds. But that's what we found is to be the best to run the lab under. And then secondly, it's best if you can begin the lab with the batteries at least partially discharged. If they're fully charged or if there's fully discharged, you will get different results than what we describe in the lab. And if you understand that and can sort of set it up for the students, that's fine. But in terms of how we set up the lab, it is with the batteries partly discharged. What I have found once I realized this is that I'll set up the equipment and turn on the light bulb and partly discharge the batteries while I'm just getting things set up for the students. And that's enough to create the situation that works very well with the lab. So the lab itself has 5 different stages of it, and each of these stages represents different conditions that the photovoltaic system with its energy storage would be operating in. And these are the situations, these are the stages that the students will be taking measurements, and so they can understand what happens with the voltage and the current in these different situations as the equipment is producing electrical energy, transmitting it and storing it and consuming it. And these pictures here on the right-hand side of the screen show the different stages. So there's one picture for each of these stages. They're in the lab itself to help orient the students to what conditions are they, is the system working under that they're taking the measurements for at that specific time. So the first condition is with all of the switches off, all the circuit breakers off. And this is not a real life situation that we're indicating here, but just basically to get some baseline measurements to find out what is the voltage of the battery, for example. That's a critical one. And so we start off in this condition 1 with all the switches off. So in the diagram here, you can see that there are red lines connecting the pieces of equipment through their switches to the charge controller. The charge controller is at the top of this picture. And it's indicating that there is no complete electrical pathway for any of these components through the charge controller. So basically everything is turned off. All the circuits are open. And in this situation, we asked the students to determine what the electrical potential, the voltage of the battery and the photovoltaic module and the load, the light bulb, what's the electrical potential in this condition. And before they actually take the measurements in the lab, the way it's set up, we ask them to predict what the value is that they're going to measure. And the reason we do this is that we found that students often hadn't thought about what the value should be, and therefore whatever number appeared on the screen of their meter, they wrote down because they had not really thought about whether that value would make sense or not. So we specifically asked them to predict what the value will be, then to measure it, and after they've measured it, to explain the value that they got or they should have gotten. So at the bottom of this slide, I also, if you're following along in the lab, this is steps 2 through 8, and there is also questions 2 through 4 that are associated with this condition. Condition 2 is the real life situation would be the nighttime with no load, with no appliance that's using the electricity turned on. So in order to create this situation with our lab equipment, we have the battery switch turned on, but the solar PV switch is off and the light switch is off. So it's nighttime, there's no power being produced by our photovoltaic module, and there's no electricity being consumed. So all we have is the battery turned on. And in this condition, the students again predict, measure, and then explain the electrical potential measured in volts of the battery. And then also the irradiance, that is the amount of light striking the photovoltaic module, and the amount of current from the photovoltaic module. Those of you who have some experience with this will say, well, that's nothing, right? There is no light striking the module, and therefore there's no current from the module. And that's the point that we're trying to get the students to realize. With the switch to the photovoltaic module turned off, there will be no current from the module. The third condition is the daytime. So now we have light striking the PV module and the PV module turned on. So it's daytime, but with no loads, no electricity using appliances turned on. So the battery switch is on, the photovoltaic module switch is on, but the light bulb switch is off. As soon as the students turn on that photovoltaic module switch, we ask them to quickly take a measurement of the electrical potential measured in volts of the battery. And the reason we ask them to do that right away is we want to have the electrical potential measurement that they can compare with measurements that they take later on after the battery has charged for a few minutes. And if this is done correctly, what they'll see is that as the battery charges, that electrical potential measurement in voltage increases. So again, we're asking the students in this condition to predict, measure, and explain not only the electrical potential measurement, but also current now from the photovoltaic module and current to the battery. And as they measure this, they will see that the current from the photovoltaic module is the same as the current going to the battery. And they hopefully will understand that the photovoltaic module generating current, and it's going into the battery, charging the battery, and being stored in the battery. Condition 4 then is still the daytime. The photovoltaic module switches on, but now the light, our load that's using the electricity, is also turned on. And so with all three switches turned on, the connections, the circuits between all three components are closed, and current can move between all three components.
I think that has some promise, you know, real world application.
So in this condition, the students measure and explain the electrical potential of the load, the battery, and the PV module, and the current of the load, the battery, and the PV module. The sizing of the different components that we have used means that the photovoltaic module by itself cannot supply enough current to run the load. So the students will see that there's some current from the photovoltaic module and some current from the battery. Added together will equal the current to the lighting load. So this, I mean, there's different ways you can set it up, and probably each of the ways has its advantages in getting students to see different aspects of this. But I think this can be an interesting way for them to understand what the electrical demands of the loads require from the photovoltaic system. Like, it may not be able to be supplied instantaneously by the photovoltaic system, but if you have a battery storage system, you can still supply those loads. Then finally, condition 5 is mimicking nighttime, but with the load turned on. So now we turn the photovoltaic switch off, but keep the battery switch on and the light switch on. And so now we are at nighttime, but we still want to use our electricity. And in this situation, again, we're asking students to measure and explain the electrical potential of the battery and the current of the battery and the load. Now the amount of current from the battery will be the same as the amount of current to the load, because in this situation, the only source of current for the load is the battery. And as students take these measurements, they will see that the electrical potential of the battery will decrease. As the battery is discharging, the voltage measurement of the battery will go down. And then that's the 5 different stages of the lab to see, you know, for students to see these electrical quantities as the battery charges and then discharges, supplying the incandescent lighting load, either by itself or in conjunction with the photovoltaic module. There are in addition, at the end, I think Scott mentioned this, some questions that we call show what you know, which ask the students to take what they've learned in this lab and connect it to other information, other knowledge that they have, or to elaborate on the information that they've learned in the lab. And this, you can obviously use or not, depending on whether your students have easily learned the stuff in the lab, or you want to give them more of a challenge, or if there's some specific people that you want to give them something harder to work on and think about. We found a couple of challenges in teaching the lab that we want to make sure to mention to you. One of those I've already alluded to, that students, without prompting, often do not have any hesitation to accept whatever number appears on the screen of their multimeters. So to address this, this is why we put into the lab, we built into the lab, asking the students to predict what the measurement will be before they take the measurement. So they're thinking about, what should I see when I take this measurement of the battery or the photovoltaic module? And then following that up with asking them to explain why that measurement was what they got, or what they should have gotten, I think is a very important aspect. So they're not just, so they're trying to develop a little deeper understanding of what is happening. I can elaborate on that if people have questions. Second, for some students, there's they're not familiar with the electrical quantities for electrical potential measured in volts, or current measured in amps. And so that can be a challenge. Certainly, if they have no understanding, then this lab won't make sense. But even for those who have learned something about it, a refresher is helpful. And one of the introductory pages to the lab includes what you see on the screen here, the Easy as Pie page that Scott put together that reviews Ohm's law and its relationship to power. So there's definitely a review built in here, which is great for those who need a reminder. And as Scott mentioned earlier, there's a whole another lesson on the Create website, which delves deeper into this material. And then third, the final challenge, which I don't know that we have a real solution for, is that using electrical potential measured in volts as a proxy for, or as an indicator of the state of charge of a battery, is an art rather than a science. And those of you who know about the chemistry of batteries will understand that the electrical potential of the battery is affected by the chemical action that has happened in either charging or discharging a battery. So to get the most accurate representation of the state of charge of the battery from measuring electrical potential, the battery would have to have not been charged or discharged for, say, 4 hours. And that's just not realistic for us to do a lab with our students. So the specific numbers being measured with electrical potential are, the trend is more significant than the actual specific number in general. So that's a little bit of a challenge to try to get students to understand that and to know how to evaluate the measurements that they're taking of electrical potential. And I think that will always be there, just because that's the nature of batteries and the electrical potential that we measure with the chemical action as an ongoing process as we're charging and discharging. It's just going to be a challenge. So it's important if you're going to teach it that you know that that challenge will be there. You'll have to do some explaining to students who are trying to understand those measurements as they take them. Scott mentioned we do have a list of materials and equipment at the end of the lab. This is in that written document, and we've also put together, because some of you may be wondering where can you get your hands on some of this equipment. So we put together a spreadsheet that's now on the website that gives you some suggestions about where vendors that you can get the equipment from, and also some prices that we put together. Not saying that you couldn't find things cheaper, but these are just some ideas for those who are looking for them about where to get the equipment. And then finally, we've seen a lot of different instructors and teachers from different programs, different disciplines who've come to our training sessions. And so we've learned from them about a lot of different ways and interesting ways that they've used the lab, or have the questions that they've used the lab to address with their students. So these are some examples in a variety of different disciplines, some related to electricity and electrical construction and engineering, and others more science-based, chemistry and physics. And then certainly, of course, the classes that are specifically on renewable energy or on solar. So there's a whole variety of different ways in which people can take the lab. On this picture, on this page that we're looking at, was a class where we actually had them building the lab equipment. So they're from just putting it together to understanding the physics of what's happening to the chemistry, right? There's a whole range of different things that, ways that you can use this in different classes. So that's all that I had prepared. Certainly eager to take any questions that anybody has, and try to answer them. While you're thinking about any questions, I'll mention that we do this training as STEM Educator Solar Institute training in 3 or 4 different locations around the United States last summer and in the upcoming summer. And if you're interested in coming to one of those, on the CREATE website, the createenergy.org website, under workshops, you'll find the information on those labs. We don't have all the dates posted just yet, but in the next few weeks, we hope to have those dates and the applications posted up on the website.
And Joel, if I could jump in here, can you hear me, Joel?
Absolutely.
Okay. It might not be that this particular lab is done at all of the workshops this summer. We for sure do it at Madison. I'm not sure about Delaware and Seattle. So if you were specifically interested in attending a workshop to get this particular lab in your hands and be trained with it, Madison is definitely the place to go, because that's where Joel is, of course. But you'd want to check to see about the other 2, what's on the agenda for those.
That's a good point. That's a good point. And there also is one in Illinois as well.
That's right, in Champaign.
Yep. So
I'd like to mention too, for just a second, while people might be thinking, there's a solid introduction to this lab, which students could read, which will help prime them for the lab, as well as a few, and this isn't common to all of the labs that I've written, all the activities that I've written, but there are some pre-lab questions that start to get them sort of thinking like what a charge controller does. And so that might help your students prime the pump, get them ready to do this lab. So take a look at the lab, please.
Are there any questions? Nope. We have one on the chat. Edward says he attended the workshop at Shoreline in Seattle, and they did work with this lab. Oh, that's good to know. Great activity. And they're going to build similar boards with their students at Arizona. Hey, that's great to hear. Thank you, Edward.
Yes, thanks, Ed.
Joel, did you do that one at Shoreline in Seattle?
Yes.
Yeah, that was with Louise. That's awesome.
Yeah. Okay, and presumably it'll be done again, but I do know that these workshops can change a little bit from year to year. So you want to double check to make sure that if you want to go to Seattle and do the workshop, that this lab, in fact, will be part of that program for this summer.
Louise was also part of our Germany Study Abroad program in May, so in Shoreline. All right, so are there any questions? No? All right, well, I guess with that, we will wrap it up, and thank you for all attending today. This webinar will be posted on the CREATE website probably by middle of next week, and I will send out an email letting everyone know that it is available. So if you, oh, Edward just said, I noticed a change in these boards, replaced the 3-gang switch boxes with the midnight solar switch. Thank you again.
Yeah.
But yes, I will.
Yeah.
I don't know if you've got something to add to that.
Oh, just Ed got to see the variation that is possible. In Seattle, we had, as he mentioned, 3-gang switch bots, which is regular switches. And then in Madison, we have those midnight solar load centers with the DC rated circuit breakers. So there's some options there that people can do, and I try to mention a few of those when we on the website. If you look at the list of the materials and equipment, so people know what some of the possibilities that are out there, if they're have certain equipment and don't have others, or if they have a budget that won't stretch to the fanciest stuff.
Yeah. No. All right. Well, like I was saying, I wanted to thank everybody for joining us today. And once this is posted on the website, I will send out an email and let everyone know that it is up there in case you needed to download it and revisit it for any information. And the list of materials that Joel has been talking about has also been posted to the website. I don't know if you guys were able to see that yet or not, but it is up there. I wish everyone a great weekend, and thank you for joining us today.
Thank you.
Have a good one.
You too. Thank you very much.
Bye-bye.
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 Bye. Thank you.
Bye.